Hello everyone, myself Prasantami Kundu. I welcome you all to this lecture of soft computing technique. This is the third lecture of module 7. In module 7, we have covered introduction of multi-objective optimization. We have done weighted sum methods and constant method. Today we will learn few more methods. The first method is the weighted distance metric method. So the weighted distance metric method is another powerful approach in multi-objective optimization that involves combining multiple objects by calculating the distance of a solution from an ideal solution Z star and then assigning weights to different objects. General approach of the weighted distance metric method. Step 1. Define the ideal solution Z star which represents the best possible values for each objective in the given feasible region. The ideal solution is typically the solution that achieves the minimum or maximum values for each objective depending on whether the objectives are maximized or minimized. Step 2. Calculate the weighted distance of each solution X from the ideal solution Z star. The weighted distance metric is given by dx equal to, this matrix is given by dx equal to summation of I equal to 1 to n wi fix minus zi star whole square. So it is dx equal to w1 f1x minus z1 star whole square plus w2 f2x minus z2 star whole square and so on up to wn fnx minus zn star whole square. So where fix is the value of the ith objective for the solution x, zi star is the ideal value for ith objective, wi is the weight assigned to the ith objective with summation of wi equal to 1. In the step 3, we optimize the weighted distance functions. The goal is to minimize this distance. It means that the solution x is as near as possible to the ideal solution Z star while the given weights and objectives. Step 4. Adjust the weights and resolve the problem to explore the trade-off between the objectives and generate Pareto optimal solutions. So the numerical example. So for the weighted distance matrix method. So consider the following multi-objective problem. So objective 1 is minimize f1x equal to x square. Objective 2 minimize f2x equal to x minus 2 whole square. Feasible region x belongs to 0 to 3. We will calculate the weighted distance matrix from the ideal solution Z star for different solution in the feasible region. So step by step, first one, define the ideal solution of Z star. So the ideal solutions, as we are going to minimize it, so their values would be f1x equal to x square is minimum at x equal to 0. So ideal solution for Z1 you can write Z1 star equal to 0. Now ideal solution minimize f2 equal x equal to x minus 2 whole square. So at x equal to 2 you will get 0. So you can write Z2 star equal to 0. So the ideal solution Z star will be 0, 0. Second is that calculate the weighted distance metric for different solutions. So we considered three candidate solutions for x equal to, for x, so we consider three candidate solutions for x in the feasible region. So feasible region is x belongs to 0 to 3. So we'll consider x equal to 0, x equal to 1, x equal to 2. For each solutions, we will calculate the weighted distance metric from the ideal solution with the following weights. So we took weight w1 equal to 0.5, w2 equal to 0.5 means we are giving importance equally to the both objectives. So now weighted distance matrix is dx equal to summation of w1 f1x z1 star whole square plus w2 f2x minus z2 star whole square. So here you can find w1 is 0.5. So here you can write that dx is equal to root 0.5 first one is x square, so x square fx is x square. Then ideal solution z1 is 0. So f1x minus z1 star whole square plus 0.5, this is w2. f2 is x minus 2 whole square, and ideal solution z2 star also 0. So that is z0 whole square. Okay. Now we need to solve this value for different candidate solutions. So here for x equal to 0, the weight distance from the ideal solution z star 0 0 is d0, which is equal to root over of 0.5. X means 0, so 0 minus 0 whole square, 0.5. X minus 2 means 2 minus 2 whole square 4, 4 minus 0, so that is root 8, that is 2.828. So that is the value of d0. Similarly, for x equal to 1, the weighted distance from the ideal solution z star 0 0 is d1. In the place of x put 1, so once again I am writing the dx, which is square root of 0.5 x minus 0 whole square plus 0.5 x minus 2 whole square minus 0 again whole square. So in the place of x put 1, so it is 1 minus 0 whole square, so that is 1, 0.5, 1 minus 2 minus 1 whole square, 1 minus 0, so we will get 0.5, 1 minus 0 whole square, that 0.5, 1 minus 0 whole square, so that is basically 1, so this is 1. For x equal to 2, in the place of x put 2, so it is 0.5, 4 minus 0 whole square plus 0.5, x equal to 2, so 2 minus 2 is 0, 0 minus 0 whole square, root 8, so you'll get 2.828. So that is a summary of the results. So that is the solution x 0, x equal to 1, x equal to 2, f1 x is x square, so that is 0, here 1, that is 4, f2 x equal to x minus 2 whole square, so that will be 0 minus 2, so that is 4, that is 1, this is 0, and weight distance is 2.828, 1.0, 2.828. So here at x equal to 1, so concludes that the weighted distance metric method calculate the distance of each solution from the ideal solution z star among the candidate solution x equal to 1, provide the closest solution to the ideal solution as it has the smallest weighted distance, that is d1 equal to 1. The solutions x equal to 0 and x equal to 2 both have a large weighted distance of 2.828. So this method can be applied to multi-objective problems with more than 2 objectives as well, using the same principle of calculating the weight distance from the ideal solutions by adjusting the weights and exploring different solutions. The Pareto front can be generated to identify the trade-off of the objects. So this is the more general form. Here we assume p equal to 2, so here you can now problem is p equal to, so that is the more general. So weighted matrix method combine the multiple objective using the weighted distance matrix from any solution from the ideal solution z star. So minimize some, we took that is this distance dx, so you can take any p and can solve it. Now the second method for today's class is lexicographic ordering method in multi-objective optimizations. The lexicographic ordering method is a decision-making strategy used in multi-objective optimizations. In this method, the objectives are prioritized in a specific order and the optimization is performed by first optimizing the most important objective. Once the most important objective is optimized, subject to the constraints imposed by the optimization of the first objective and so on, this method assumes that the decision maker has a clear meaning of prioritize among the objects. The solution process proceeds by treating the objectives in a hierarchical manner. Basic steps of lexicographic ordering: prioritize the objects, so rank the objects in terms of the importance. For example, if there are two objectives f1 and f2, then it is to be decided which one is more important. Okay, suppose we have f1, f2, f3, and so on. So we will decide which one is which one is most important. Suppose f1, then we'll perform the f1, then with the constant we'll perform f2 and so on. So optimize the first, that is most important. Optimize. Solve the optimization problem considering only the first objective, ignoring the others. Optimize the second objective. Once the first objective is optimized, optimize the second objective subject to the optimal value of the first objective. Similarly, continue for all objectives. Repeat the process for all objectives in order of their importance. So example, so we are taking two functions, so two objective optimization problems. So let's consider a two objective optimization problem to demonstrate lexicographic ordering. So objective 1, minimize f1x equal to x square. Objective 2, so that is minimize f2x equal to x minus 2 whole square. Feasible region is x belongs to 0 to 3. Assume that the decision maker prioritize f1 over f2, means first we'll do f1. So we'll first minimize f1x, and once the optimal value of f1x is found, we'll minimize f2x within the feasible region defined by the optimal f1x. So let's discuss step by step. Step 1, optimize the most important objective, that is f1. So f1x equal to x square, so minimum value will be at x equal to 0, so f1x minimize at x equal to 0, and the minimum value of f1 is f1 0, so that is 0. Step 2, optimize the second objective f2 subject to f1, so we need to evaluate f2x for x equal to 0. Thus the value of f2 at x equal to 0 is 4. So step 3, final solutions. To find solution for the multi-objective problems using the lexicographic method is at x equal to 0. So f1 0 equal to 0, f2 0 equal to 4, f2 0 equal to 4. This means that the optimal solution prioritize minimizing f1 first and then minimize f2 as much as possible. So in problems with more than two objectives, the lexicographic ordering can be extended in the same way by sequentially optimizing each objective in a order of their importance. So the third method is the reference point method. The reference point method is a multi-objective optimization technique used to convert a multi-objective problem into a single objective problem by introducing a reference point. The method uses the reference point, which represents a target or expression level for the objectives, to guide the optimization process. Key concept of the reference point method. The one reference point. So a reference point R equal to R1, R2, Rn is selected by the decision maker. Each Ri represents the desired target value for the corresponding objective Fix. So for the target value of Fix equal to Ri. Similarly for the other value. Step 2, deviation from the reference point. So the method minimizes the deviation from the reference point for each objective. The deviation is computed as the distance between the reference point and the actual value of the objective function for a given solution. Scalarization is the third step. So the method usually involves scalarizing the multi-objective problem into a single objective by minimizing the weighted sum or some other distance measured between the objectives and the reference point. So general formation of the reference point method. For a multi-objective optimization problem within m objectives, that is f1x, f2x up to fmx, and the reference point is r equal to r1, r2, r2, rm, the reference point method minimizes the weighted distance from the objective to the reference point. The scalarization of function often take the form minimize zx equal to summation I equal to 1 to m wi fix minus ri. So we need to minimize zx equal to summation I equal to 1 to m wi mod of fix minus ri is the reference point. We need to minimize it, where wi are the weights assigned to the objective reflecting their relative importance. Fix is the value of the ith objective and ri is the reference point, that is the target or experiential level for the ith objective. So numerical example of reference point method. So objective 1, minimize f1x equal to x square, minimize f2x equal to x minus 2 whole square. The feasible region is x belongs to 0 to 3. Step 1, define the reference point. So we are defining the reference point r1 equal to 1. So this is target for the first objective. R2 equal to 1, target for the second objective. So the reference point R is 1, 1. Step 2, formulate and scalarized objective functions. So for simplicity, consider equal weights. So we are considering equal W1 equal to W2 equal to 1. So now Zx equal to, as I said, Zx equal to summation I equal to 1 to m wi mod of fix minus ri, that is the reference point, is weight. So here weight is w1. So there are two functions. So here m equal to 2, w1 equal to 1, w2 equal to 1, r1 is also 1, r2 equal to also 1, and f1x equal to x square, f2x equal to x minus 2 whole square. So here we'll get summation w1 fix ri, so that is f1x minus w1 equal to 1, so it is mod of f1x minus r1 plus f2x minus r2. R1 value is 1, r2 value is 1, so it is mod of x square minus 1 plus mod of x minus 2 whole square minus 1. Thus the problem is to minimize zx is equal to, so the problem is zx equal to mod of x square minus 1 plus mod of x minus 2 whole square minus 1. So for x equal to 0, we need to evaluate zx for different values within the range. So range is from 0 to 3. So we'll take x equal to 0. So f1 0 is 0, that is x square. F2 0, x minus 2 whole square, 0 minus 2 whole square, that is minus 2 whole square, 4. And z0, now take the value here. So it is 0 minus 1 plus 4 minus 1, so that is 1 plus 3, so that is 4. So the value at x equal to 0, the zx value, so that is z0 equal to 4. So that is z0 equal to 4. Now at z equal to 1, so at z equal to 1, you will get it 1 minus 1 plus 1 minus 2 whole square minus 1. So you will get it 0 plus 0, so that is basically 0. Again at x equal to 2, f2 equal to 4, so you will get f2 equal to 0. So for x equal to 2, f1 2 equal to 4, f2 2 equal to 0, so z2 will be 3 plus 1, that is 4. For x equal to 3, so that is 9 minus 1, f3 is 9 minus 1 plus 1 minus 1, so that is 8. So at z3 value is 8. So step 4, find the optimal solution. So for x equal to 0, f1x 0, f2x is 4, zx is 4. So at x equal to 1, f1x 1, f2x equal to 1, zx equal to 0. At x equal to 2, f1x is 4, f2x is 0, zx is 4. At x equal to 3, f1x is 9, f2x is 1, and zx is equal to 8. So the minimum value zx occur. The minimum value of zx occurs at x equal to 1 or z1 equal to 0. Therefore, the optimal solution is at x equal to 1, where both objective f1x and f2x are exactly equal to their respective reference values, that is r1 equal to 1, r2 equal to 1. Conclusion: the reference point method successfully converts the multi-objective optimization problem into a single objective problem by minimizing the deviation from the reference point. So conclusion, I hope you have understood the three methods. One is that weighted distance matrix method, second lexicographic method, third is the reference point method. So the question for today's class is that to minimize f1x equal to x square minus 3, f2x equal to x minus 4 whole square, x belongs to 0 to 7. So solve these questions by all these three methods. So these are the references for today's class. Thank you.